Okay, welcome back. In the last video, I talked about the method of joints as one of the two methods that we had available to us for solving truss problems. Just as a review, what's a truss? Truss is a, here we go, here a truss. So two force members connected at ends only, and applied forces only at the joints. That's what a truss is. And we talked about the method of joints to solve these problems. The method of joints. And what's the method of joints? Each pin gives us a free body diagram, and each of those gives us two equations of equilibrium. And it turns out that for any truss system in two dimensions, which is what we have here, two-dimensional truss system, that this will always allow us to solve for all of the internal loads, which means the internal loads on each of these connections or members, right? Whether or not that it's in tension or compression, and will also allow us to solve for the reactions. There's another way of doing it. So this is number one. The other way of doing it, in number of two, is called the method of sections, which is abbreviated MOS, method of sections. The method of sections does for us, it also allows us to solve truss problems, but we're not required to find every single load on every single member when we use the method of sections. So here's the example that I had worked through or talked about in the previous video on the method of joints. But we can also approach this by the method of sections, and perhaps all we really care about is, let's say, the load that's right here on this particular member CD. Maybe this bridge has been designed previously, but the records have been lost, and in some storm damage, you've noticed that C and D has been damaged to some extent, the member that goes from here to here, and so you need to very quickly find out what loads it's being subjected to so you can determine if the bridge is still safe or not. Okay, so that's, maybe one concept. So just like before, we're going to take our real-world situation and we're going to draw some free body diagrams. Well, this time, instead of picking out the joints, the joint at A and C and E and D and B, we're going to do what we call section this truss. So I'm going to draw an imaginary line, okay, right here that goes through AD, CD, and CE. And I'm going to draw a free body diagram of everything that's on the left side of that line, okay? But I'm not going to draw the members that I've cut. So basically everything that's to the left of this dotted line, this little orange dotted line, but not including the members that I've cut. So let me do that real quick. So here is the member that goes from A to B. Here's the member that goes from A to C, and here's the member that goes from B to C, okay? So once I've drawn that, that's my free body diagram. So basically I said, here's a dotted line, let's draw everything to the left, free from the universe, right? We're going to break that piece of that free body, or that free body, free from the rest of the universe, okay? Then we have to do just what we would do for any other free body diagram. We have to represent everything that we've cut, right? Everywhere we've broken it free from the rest of the universe by forces. So right here at B, we see that we have a roller that's going to apply a force in this direction. Over here, we have a member attached that we haven't drawn. And that member is A to D. It's a two-force member, which lets us know that the direction of the force has to be in the same direction as the member goes. So line of action of the force has to match up with the direction that this member goes between A and D. I'm going to draw it in tension because I don't know whether it's in tension or compression, so I'll draw it in tension and I'm going to call it AD here, right? Same thing down here, C to E. I have a force in tension, and also C to D. I have a member I don't know any better. I'm going to draw it in tension. So little dotted line, everything to the left, and then I'm also going to do the same thing, but I'm going to do everything to the right. Now this is going to be look a little funny, but it's just as valid. Oops, I forgot to label. This is the force P, that applied force P. So we still have the applied force P. We still now down here have EY and EX, which again I've drawn in the positive directions because I don't know which direction they should be. But here I have AD, and I have in this previous drawing drawn it in tension. I haven't verified that it's not in tension yet, so I'll go ahead and leave it in tension, right? So this is now in tension on this side. Same thing for the CD, and the same thing for the CE. Right? So now I'm going to go from there to equations of equilibrium. Now, this is a rigid member, or a rigid body, in 2 dimensions. That means I can write 3 equations of equilibriums for, let's call this free body of the left. And I can also write 3 equations of equilibrium for the free body on the right side, right? And so altogether I'm going to have 6 equations of equilibrium. If I count unknowns, I have BY, EX, and EY, and I have AD, CD, and CE. So once I've written these 6 equations of equilibriums, here are the unknowns that are contained. Oops, that's an A, sorry. I can solve for all of these. So by using this method of sections, I can write fewer equations, right? Keep in mind, when I did method of joints, I went it with 10 equations and 10 unknowns. Here I have 6 equations and 6 unknowns, which is some improvement, not dramatic, but some. But what I've gained in terms of fewer equations, I've lost in terms of understanding. For example, I do not know, once I'm done here, 4 pieces of information. I don't know what member AB is being subjected to, or BC, or AC, or even DE. So, method of sections, this method of sections is very powerful. Cases when you only need some members for trusses. When we look at frames and machines, someone can write that down. We're going to talk about them in this video. Frames and machines. You'll see there's actually methods of sections that's more valid or more valuable to us than the method of joints. So for method of joints and method of sections, both apply to trusses. And you should learn to solve 2-dimensional trusses. That's what I'll spend all the class time and homework time and lecture time and the next test on in terms of trusses, 2-dimensional trusses. We'll learn that method of sections becomes valuable to us when we talk about frames and machines, which is the second part of Chapter 6. Between the first part of Chapter 6, 2-dimensional trusses, and the end of Chapter 6, frames and machines, there's a section on 3D trusses. Okay? I will not cover this in class. I will not prepare a video about it. I will not ask homework questions about it. But on the final, there will be one question on 3D trusses. So again, please remember, this is very important. Please remember that even though I'm not going to cover this or assign a homework on it, you are responsible for learning how to do 3D trusses. If you'll spend a little time, and actually not very much time at all, you'll recognize that you use method of sections and method of joints. It's just that now instead of getting 2 equations or 3 equations for each free body diagram, you're going to get 3 equations or 6 equations for each free body diagram. So things are a little more complicated, but nothing conceptually different than what we've covered here. While I will not cover any of this in class, if you need help, you can come and talk to me during office hours.